So this lecture is going to be about estimating the sum n less than x of 1. Now, I know what you're thinking, but bear with me. So the way we're going to do this is we're going to look at the inverse Mellin transform of the Riemann zeta function. So let's look at this integral 1 plus epsilon minus it to 1 plus epsilon plus it of zeta of s x to the s ds. And this sort of construction should be familiar from the Bernoulli's formula lecture, right? We're doing that construction. So because we're in this region of absolute convergence for the zeta function, we can replace it with its series definition. So this is 1 over 2 pi I integral 1 plus epsilon minus it to 1 plus epsilon plus it sum n from 1 to infinity of 1 over n to the s x to the s ds over s. And so this Dirichlet coefficient 1, that's the thing that we are summing over here. So using Bernoulli's formula, we immediately get that this integral is equal to the sum n less than x of 1, the sum of these Dirichlet coefficients, and then the error term we get is O of x to the 1 plus epsilon over t. And later we'll choose a t that's some power of x to optimize this error term, but for now we'll just leave it as t. And so this was covered in the lecture on Bernoulli's formula, so if you're not familiar with this, maybe check that out. So the second way of evaluating this integral that we're going to be talking about in this lecture is just using the analytic properties of the zeta function. So zeta of s has a pole at s equals 1 with residue 1. This is something you can look up. And so if we want to look at this integral 1 plus epsilon minus it to 1 plus epsilon plus it zeta of s x to the s ds over s, we can consider this contour. So here we're going to take, maybe slightly poorly drawn, but so here we're going to take this bottom corner to be 1 plus epsilon minus it, 1 plus epsilon plus it, and then for the other side of the rectangle, I'm going to take it to be 1 half plus epsilon plus it, and this will be 1 half plus epsilon minus it. And so let's give these segments names. So this is going to be C1, C2, C3, and C4. And we have one pole in this region, this one. So this pole at S is 1. Okay. And Cauchy's residue theorem implies that the integral C1 plus C2 plus C3 plus C4 of zeta of s x to the s ds over s is going to be, so of course x to the s ds over s has no poles in this region, so it's just going to be, well, let me put 1 over 2 pi I here. Pi is going to be equal to the residue at s equals 1 of zeta of s x to the s over s, which is just x. Okay, so this integral along C1 is what we're interested in. So let's remind ourselves why we're interested in this. Well, it's because using Perron's formula, right, this integral along C1 is giving us the sum of integers that we're interested in estimating, right? Our task for today is estimating this quantity, and Perron's formula tells us that the integral along C1 does estimate this quantity. So we're trying to get an expression for this, and we've got an approximation that it's about x. So our task now is going to be bounding the integrals along C2, C3, and C4. So let's do that. So for C2 and C3, recall the convexity bound. So the convexity bound, as discussed in that lecture, is that the Riemann zeta function, zeta of sigma plus it, is at most t to the 1 minus sigma over 2 plus epsilon for sigma between 0 and 1. So let's use this in integral for C2. So the integral C2 of zeta of s, x to the s ds over s. When we bound this, this is going to be an integral. We're just going to think about this as an integral in sigma. So it's going to go from 1/2 to 1, or 1/2 plus epsilon to 1 plus epsilon. And then for the zeta function, we're just going to use the convexity bound here. So this is going to be t to the 1 minus sigma over 2 plus epsilon. And then here we have an x to the sigma, right? The absolute value of x to the s is x to the sigma. And then we have a d sigma over, and then here we can just have t, right? That the absolute value of s is at least t. Okay, and then this has an elementary antiderivative, so you can just write down what it is, but the shortcut is just to look at both endpoints. So what you end up getting at the right endpoint, well, this t power essentially vanishes, right? You get x to the 1 plus epsilon, and then you have a t to the minus 1 plus epsilon. And then at the left edge, you end up getting x to the 1/2 plus epsilon, and then you have a t to the 1/4 minus 1, so this is going to be minus 3/4 plus epsilon. Again, you can, this has an elementary antiderivative, so if you want to do it carefully, you can do it that way. And of course, C3 is similar. Okay, what about C4? So integral along C4 of zeta of s, x to the s ds over s. Here we're going to have an integral in t. So again, using the convexity bound, on the critical line, essentially, it's going to be t to the 1/4. So that's right. T to the, well, let's be a little bit careful, right? We can write t plus 1 to the 1/4 plus epsilon, just because when you're close to the real axis, the convexity bound isn't telling you you're going to vanish or anything. It just tells you you're bounded. So you have this, and then here you have an x to the 1/2 plus epsilon, right? There's the absolute value of x to the s doesn't vary as we're going up and down this vertical line, and then we have a dt over, and then the absolute value of s is sort of t, but I don't want to write over t because that might be weird when t is close to 0, so I'm going to write plus t here. And it's going to be integral from minus t to t. So we're integrating along this vertical line. And again, here, you more or less have an elementary antiderivative, right? You know, when there's no plus 1 here, you have an elementary antiderivative, and then you can just take out some chunk around the real axis just to make sure that nothing's blowing up. And what you end up getting is that this integral is bounded by x to the 1/2 plus epsilon t to the 1/4 plus epsilon. Okay, so those are our bounds. So let's put it together at this point. So to recap, the first thing we did was use Pavlov's formula to say that the integral along C1 was this thing. So the thing we're interested in, some n less than x of 1, was equal to 1 over 2 pi I integral along C1 of zeta of s x to the s ds over s, and then the error term Pavlov's formula gives us is x to the 1 plus epsilon over t. And from Cauchy's residue theorem, right, we get that the integral along all the parts is x. So this is going to be x is 1 over 2 pi I, the integral along C1 of zeta of s x to the s ds over s, and then we have the C2, C3, and C4, and we've bounded these up here, right? So C2 and C3 gave us x to the 1 plus epsilon t to the minus 1 plus epsilon plus x to the 1/2 plus epsilon t to the minus 3/4 plus epsilon. And then the integral along C4 was x to the 1/2 plus epsilon t to the 1/4 plus epsilon. Okay, and putting these two things together, what do we get? We get that the sum n less than x of 1 is equal, so these two terms are equal, so let's just replace this with x and carry over the error terms. So we have an x to the 1 plus epsilon t to the minus 1 coming from Pavlov's formula, so that's this term right here. And then we have x to the 1 plus epsilon t to the minus 1 plus epsilon plus x to the 1/2 plus epsilon t to the minus 3/4 plus epsilon. So these two come from segments C2 and C3. And then finally we have this term, x to the 1/2 plus epsilon t to the 1/4 plus epsilon, and this term is coming from C4. All right, and we want to make this error term as small as possible, of course. So we're going to choose a value of t that's a function of x to optimize the size of this error term. We want to make it as small as possible. So we're going to take t to be x to the alpha such that, so this, when I write st, this means such that. This is an abbreviation I'm going to use quite often. So we can take t to be some power of x such that this is minimized. And how do we do this? This is called balancing error terms. So balancing error terms, the idea is that if you look at just, say, this first term, x over t, more or less, that makes us inclined to take t to be very big, because then we're dividing by a big number. But if you look at this last term, we've got a t to the 1/4, and that incentivizes us to take t to be very small, because we don't want to take t to be huge, because then we're multiplying by a huge number. So once we make the substitution, t is x to the alpha, our error term becomes x to the 1 plus epsilon t to the x to the minus alpha. This second term here is going to be x to the 1 plus epsilon times x to the minus alpha plus epsilon. Here, you might want to write x to the epsilon alpha, but epsilons they change value from line to line. It just means some small and positive real number. Third term here is going to be x to the 1/2 plus epsilon, and then we have x to the minus 3/4 alpha plus epsilon, and then this last term, C4 here, we have an x to the 1/2 plus epsilon, x to the 1/4 alpha plus epsilon. And we want to minimize this. And okay, through some inspection, we can see that we can ignore this term. We can drop it because it's just smaller than this term, right? We still have this x to the 1/2 plus epsilon, and then here we have an x to the minus 3/4 alpha, and here we have an x to the 1/4 alpha. And we're thinking of t as being large, so alpha is going to be positive, so this term is just always smaller than this term. And similarly, this term is always going to be smaller than this term, but they're similar enough, and we're going to ignore the epsilon, so that doesn't matter. But what this means is that we end up with just two terms to compare. Oops. So the way that we're going to balance error terms is we're going to take this term. So this is 1 minus alpha is the power, and we're going to set it equal to the power here. So the power here is 1/2 plus 1/4 alpha. And again, the idea is that if to make this power small, we want to take alpha to be very positive, and to make this power small, we want to take alpha to be 0. We can't take it to be negative, because then stuff stops making sense, but this term wants alpha to be small, and this term wants alpha to be big. Once we make the powers equal, then we're doing as good as we can do, right? If we were to pick an alpha that weren't optimal, then one of these two error terms is going to be bigger than the other, and then we might as well shift, make the big one smaller at the expense of making the smaller one bigger, because the smaller one already wasn't contributing asymptotically. So anyway, we have this equation. The solution to this is alpha is 2/5, and what that means is that our error term is going to be 1 minus 2/5, so 3/5. You can also put it in here. You see you also get 3/5. So that implies, just remembering where we're coming from, right here, that the sum of integers less than x over integers less than x of 1 is equal to x. That was our main term coming from the residue. And then substituting in t is x to the 2/5, the error term we end up getting is big O of x to the 3/5 plus epsilon. And yeah, okay. And this is not great. Sometimes you can do better than this kind of result, but this is all right. And so let me show you how you might do better by assuming the Lindelof hypothesis. So So let's do it again. Well, assuming the Lindelof hypothesis. Okay, so it's going to be the same strategy for simplicity. We're going to look at this rectangle from 1 plus epsilon plus it to 1 half plus epsilon plus it to 1 half plus epsilon minus it to 1 plus epsilon minus it. Again, we have our pole at s equals 1. It's also the same story. C1, C2, C3, and C4. So the Pagelsdorff formula stuff is exactly the same. The C1 stuff is exactly the same. The sum of the residues is all the same. So it's really just the bounds on C2, C3, and C4. So let's redo those, assuming the Lindelof hypothesis. So let me remind you, the Lindelof hypothesis is that zeta of sigma plus it is less than t to the epsilon for real part sigma between 1 half and 1. Okay. So the integral along C2 and C3 will be similar. So these horizontal segments at the top and the bottom of zeta of s, x to the s ds over s. Here, so we're going to integrate from 1 half plus epsilon to 1 plus epsilon. So this is sigma, the real part, is going to be varying between these 2 points. And to bound zeta, we're going to invoke the Lindelof hypothesis. I'm going to say this is at most t to the epsilon. And here we've got our x to the sigma. And here we have a d sigma over t. And this is going to be x to the 1 plus epsilon t to the minus 1 plus epsilon. Okay. And the integral along C4 of zeta of s, x to the s ds over s, this is going to be integral from minus t to t of, again, invoking the Lindelof hypothesis. This is going to be t to the epsilon, or t plus 1 to the epsilon if you're worried about behavior along the real axis. I'm taking a bit of a shortcut here. X to the 1 half plus epsilon dt over, you know, I will write 1 plus t just to be safe. And then this is x to the 1 half plus epsilon t to the epsilon. So you see that we're getting better error terms, right? Before this contribution from C2 and C3, instead of a minus 1 here, we had a minus 3/4. And here, instead of a t to the epsilon, we had a t to the 1/4 plus epsilon. So we've saved a t to the 1/4 in both of these. Now again, summing up, what we end up getting is the sum n less than x of 1 is the sum of residues. This is, and then we have the contribution from Pagelsdorff's formula. So that is x to the 1 plus epsilon over t. And then we have from C2 and C3 an x to the 1 plus epsilon t to the minus 1 plus epsilon. And then the C4 contribution is x to the 1 half plus epsilon t to the epsilon. And there's no real worry about balancing error terms here. There's no serious growth in t, right? The only serious growth in t is this t to the epsilon. So we can just take t is about x. In Pagelsdorff's formula, you don't want to take t to be bigger than x because some funky stuff can happen. So, but taking t as x is good enough here. And what that gives you is the sum of n less than x of 1 is x plus O of x to the, and this is the term you're going to get. This is the term that's contributing. So x to the 1/2 plus epsilon. And you see that this is better, right? So before we got x to the 3/5 plus epsilon without Lindelof. And if we go back and do a bit of retrospective, think about where we're getting this error term. The main contribution came from this integral along C4. Right? The integrals along C2 and C3, they had it divided by t. They weren't very big, but this integral along C4, that had a t to the epsilon. And this is typical. Usually it's this left edge that's going to be your bottleneck. That's the thing that's going to give you a big error term. When you take this and you try and balance it against what you get from Perron's formula, the top and bottom segments end up not being an issue usually. And the Lindelof hypothesis really helped us because it meant that our error term was smaller because our integrand was smaller. So our estimate of the integrand along C4 and also C2 and C3 was smaller than what we had gotten without the Lindelof hypothesis. And that means that C1 was more of the contribution of the sum of residues. And this integral along C1 is also what was giving us our left-hand side in Perron's formula. So this is a general thing that happens, that if you can get better bounds on the growth of your L function on vertical lines, then you can get better estimates for your sum of Dirichlet coefficients. Proving the Lindelof hypothesis is very far out of reach. For now, there are some subconvexity bounds that exist for a variety of L functions, so you can sometimes make use of those. You can also prove average Lindelof hypothesis type results in a lot of circumstances, and we will do that later in the course. That's quite difficult, but it does improve results quite a bit, and something that people do. So this is and sometimes you may just want to assume the Lindelof hypothesis depending on what you're trying to do. Maybe you just want to know, like, actually how fast does it grow, and assuming the Lindelof, there's a good chance of giving you something that's closer to the truth.